हम्म, इस मेरी तरीके तो ये है फीलिंग है। कुछ ऐसा किया था मीटिंग होगा तो सदन में कभी पूछ सकते हैं।
कौन बोला है?
ठीक है।
मिशिगन साहब को देने के लिए बोलो ना, इससे बात करते हैं।
मुझे मिसी का हो गया है, मैं बोल रहा हूँ एग्जीक्यूटिव चाहे तो एग्जीक्यूटिव भी कर सकता है, बोल रहा हूँ।
हमारे हुआ मेरा ना
Six was all about white sense, where we talked about the Doppler temporal time dispersion. So there was the six section how to use MGF of SNR to analyze the performance of channel model as white sense scattering. Concepts is like we have to first then scattering function. Then we will talk about the power delay. Then MGF part 2 will like out and the capacity. That is the aim. So problems will talk about channel concept, time varying and input output and as YT is HT tau WT. A wide sense stationary WSS the predicted value of H of t and for time lag delta t. So the uncorrelated scatterings, the delays are uncorrelated. In that case, if the delta t here, they at the same time tau 1 and tau 2 goes to see delta t the tau 1 delta tau 1 minus here this is the relation for our which implies that different tau fade independent and it's in stationary RH of tau 1 and HT H plus delta t tau 2 is equals to R basically delta t H if you see the conjugate in signals then in that case whether autocorrelation uh, whether we are having this delta t tau 1 tau that's where this is scattering function scattering function yeah the scattering function there this H delta exactly is how you can transform the H delta theta exactly right here you are integrating with it by f into delta t of delta t there this power delay profile will be simple integration of the scattering function having the power what you will observe is that it is if delta t equals then it is equal to power delay profile Doppler spectrum. Hi, Cellular.
మమ్మీ మమ్మీ నీకు ఒకటి తెలుసా మమ్మీ అభి ఎప్పుడు యాక్టింగే కదా
ఉళ్ళమంట
ఉత్తుత్తికి ఏడ్చేస్తాడు ఓ ఇట్లా చిన్నగా
Transfer function, since it's just the full edge of here you are having as well as tau. Tau is actually the one time and another that is equal as it is height sensitive time lag of delta t. So this WSSUS links just get the expected value of part of h of t f square is integration of the summation of power delay tau at the function h. Now you may ask how to calculate the average error probability by a moment. For several modulations, the error probability can be written m of gamma divided by sine square, where the constants depend on the like for the BPSK and the KSK, the is equals to pi. For the m, p at pi by m. So if we calculate the outage at threshold, the p of out probability equals to the CDF function gamma. The CDF is equals to the probability of gamma less than or equals to gamma t. That is nothing but CDF function. So CDF function is directly calculated with the inverse Laplace transform of, since Laplace is there, that's why S term is there, where S is equal to plus j omega, right? All several ergodic capacity is nothing equal expected value of why it is expected plus 1 plus gamma, which is SNR, is random in nature. Normal, then we will now for the narrow band signaling over flat fading per symbol, gamma is bar multiplication with part of H naught square, where H naught is the complex Gaussian sample. So where what does H represents? There's nothing but the fading. In order to calculate the outer narrow band say flat fading distribution is nothing but for a small for frequency selective fading with FDM, the burst subcarrier SNR depend on H of FK, because here the frequency selective, then the frequency selective fading will when we are having the code and signal reaches having more than this band, and if it is greater than B frequency selective, that's where the represent MZF based supply era that last time we so there's one problem like just to calculate it. There are several to this classes calculate. So given a relay fading and every and it is a BPS scale. Average BER for the relay, it is nothing but M of count divided by what S of count. The BPSK P 0 to pi just having and if you calculate and I didn't just integrate so if you had a data you're our 8 is equal MGF is equal MGF for M is equal to for Nakagami M the C 1 minus M is equal to F of capacity is it is in the and 1 minus and the transformation have to do exactly is this spread doesn't but it alters core for fixed gamma bar larger M less C is equal leading to higher capacity. So this WSSUS via SHF. So basically, you're having WSSU there it is all H delta T tau 1, which is a key a PDP pH of tau and the plus MGF in a this capacity for rated plug section was. So here we're going to so for the basic frequency, you know, voice is having where voice is a subset of audio. And basically FM is 8 and amplitude model one channel is equal. These are the stuffs that we already know. Now MIMO is like the basic concept about where MIMO can be spatial multiplex. Whereas OFDM, as we know, data parallel where the wideband channel is split and parallel to serial that is a cyclic triple. Then after cyclic triple parallel where the parallel it will be in an NFFT. Finally we'll have multiple basis of CDMA is used PG here we are having CDMA 384 5 to 30 memory. WC Wildman C and HSD high speed evolution data object. Having LT IMAX world of interoperative applications. Data rate increases. But the challenges here, as this course itself started with that, here we are having the base, here we are having line, multiple signal components, line of sight can lead to or destructive interface. So aim is to develop a model for multiplication. So here we are having the output YT, wireless channel HT, here wireless channel is. Whereas in some cases HTH is also repeating coefficient. H not will definitely. So ith path of wireless channel is characterized by delay and attenuation. So which is I delta T tau I. Okay. So multipath scenario, you are having 0 L minus. Each path is having amplitude as tau no delay created with first component. Okay, so multipath response is the individual response. So this HT, is nothing A naught delta T plus A1 delta summation AL minus 1 delta T minus tau L. The impulse response of wireless channel path informant summation of 0 to L I delta T transmitted signal part of STE per and here you're multiplying and getting with respect to carrier frequency. So the passband signal after modulation, that is SPT. So FC is around 900 meg for 3G or 4G. Remember what is FC? 900 meg 5 gigahertz. As we know, for path it is ST because it is HT. It is convolution in time. Any convolution with respect to delta function is shifted by the same amount. So YP of AS multiple L minus AI is minus tau ST minus T2 pi because here we are keeping up. So we see this is a carrier signal received baseband signal. So the complex received baseband signal. We remove this carrier away. Why carrier was required here? Because carrier was required to transmit the normal baseband signal. Now we were talking about a passband signal. After passband signal, when the carrier is removed, the complex baseband receives signal is nothing. Summation of I is equals to L minus S T minus tau I e power minus J 2 pi FC tau I. where it is multiplied by power. This is the carrier which got removed. This baseband signal, receive signal. Now for the narrowband signal where FM is very less than. So the ST minus tau is almost equal by in case of GSM it is 900 megahertz. So why that is the key? Because the delay is inversely proportional. So around 2 microseconds the delay will be there. So this is very less. So for the narrowband signal, we remove and and this the complex coefficient. This is called multipath coefficient. Sorry, fading coefficient. So you remember this where ST was the impulse response, but here why what is H here called? Is H here called? So H here is the fading coefficient, complex coefficient which is fading coefficient. So here it is equals to AI e power minus j 2 pi fc tau I, where fc is the carrier frequency, and H is equals to summation of. It is not T. It is not a. So I is equals to L minus AI e power j 2 pi. YT is equals to H into ST, depending on the attenuation. So how we started first? HT was uh, summation of I is equal to L minus I delta, right? This was the impulse response multipath, because L was a number of multipath. That was the case. Now next was HT. Now we calculated ST, where is a transmitted passband. ST was transmitted passband where I IP of real part of this is a transmitted passband. Transmitted. The transmitted passband. After transmitting it to real signal, so this is the SP of here we are talking. So YT is nothing but YT is nothing. Once we convolve it, real part. Let, let us just let's say not they have not real they have assumed X space. Now keep this out. The Y at T1 the receive this HI. That is what is, and this is the Modulated signal to receive pass a complex baseband signal is this one. So any signal coupled with the shifted by the signal on it. Let us say L is things not even. If you say assume A not A1 is tau 0, tau 1 is keeping the H value, there's nothing. So here it is happening just structure interface. Then tau 0 is equal H is structure interface, which enhances the signal amplitude. Coefficient H varies the biggest channel. Coefficient H varies depending on channel tau I. So the fading coefficient, the H is a channel fading coefficient. The complex number. Some I AI fading channel fade that to time power of the fade. This fading process, which causes the received signal to vary as an input to the wire. So we need to develop models for fading channel. Fading channel coefficient H is equals to combination of L minus AI e power minus is equals to sorry, which equals to summation of I is equals to 0 cos 2 pi fc. We can in terms of cos. Sorry. So this is x and y. We will interpret it for how this h is interpreted. H is equals to x plus j y, where x is equals to ai cos 2 pi, y is equals to ai sin pi fc tau. So since ai and tau are random, x and y are the sum of a large number of random. ai and tau are the constant. The central limit x and y can be assumed to be Gaussian because it is a sum of all. And ai and tau are also random in nature. Random, then we sum it to infinity. Large number of random L if it is large number of multipath coefficients exist. In practice they exist. So if we sum it to a large number, then it leads to a limiter that is assumed to be Gaussian in nature. Okay. So fx of x, it is having this and sigma as a random e power minus x minus. Suppose x and y ranges from 0 and sigma is equals to 1 by simply by e power y is equal to, assuming x and y independent, fx by why it is independent, can you tell me? First of all, it is sine and cos. Both are independent, equal to this. So fxy is equal H is equals to nothing x plus iy if it's assume it is a in power a5, where a is nothing but h was written. First of all, h was plus iy. We can also write a power a is not plus y square as it is written. Y is equals to tan inverse. So if x is equals to a cos phi, y is equals to a sin phi, as we have written like that. So in that case, fx of phi, x and y, which we can represent in terms of a phi. Here just ignore what is x and y. So we are trying to map. So in order to convert into x Cartesian to exponential format, need to convert from Jacobian matrix. Fx of y is equals to Jacobian of xy mod of Jacobian of xy. Want to convert from x to phi, so we need to differentiate with respect to phi. Really, x where, uh, where x is equals to y is equals to j of xy is a. So f of a phi in terms of this is equals to a by pi minus a square. A by pi e power minus a square. So joint distribution in terms of magnitude and base component. Marginal distribution f of a. How will you calculate? Integrating with respect to opposite variable. F of a of phi, function of a phi. D phi is equals to pi by pi. Why? Because phi is anyhow pi by 2 pi. Or you can tell 2 pi. Integration over marginal distributions. A e power minus a, which is a Rayleigh distribution. A e power, and the channel coefficient H is also termed as a Rayleigh fading, where f of a is equals to a e power. So when a is very very less than or tending to, and in that case it is a D fade. So my aim was to tell you how this H. First we started with impulse response. Then if once we got in impulse response, then calculate from the passband signal, receive passband signal. Out of passband signal, we took that a receive baseband signal. In the receive baseband signal, we for the narrowband signal approximated with respect to HT. Once we approximated with respect to ST, then we got this H, okay, where H is nothing but summation of 0 to L minus AI e power minus j 2 pi f tau I, right? So that was the main intention. Now in H, we calculate in terms of xn plus iy. If we calculate xn plus iy, both we told that if we sum it with respect to infinity or the multiple parts, then it is leading to the Gaussian. Then with Gaussian also we calculated with respect to mean and the variance. Once we had mean and variance, then we convert into a e power j5. Then we calculate a e power j5, which is showing this amplitude part as well as phase part. In that case, the amplitude part was found as 2a e power minus means then x and y are independent. For example, here we have assumed x and y are independent. What if we would have assumed x not independent? To expect that it will be Rayleigh. Here the assumption is they are independent. Why? This leading to 1 of pi e power minus pi plus pi square. Also, x and y are having 0 and 1 by 2 sigma square. So here it is simple multiplication, and out of which we took h. So when a is 2a e power minus a square is all f of, this is a PDF, f of f a of a, where different multipath channel cancel out each other, the high attenuation. So h is equals to a e power j5. So a f of a pi a of phi, a by pi. Simply if you calculate the Taylor density, if you calculate the marginal distribution of phase, it is equals to 1 by 2 pi. A by pi e power minus is equals to 1 by 2 pi. So it's very interesting actually. The Rayleigh fading coefficient, the amplitude of that the channel fading coefficient h is Rayleigh distributed, whereas the phase is uniform distribution of value of 1 by 2 pi, where phi ranges from pi to minus pi to pi. Uniform distribution. Very interesting. So f a of a is equals to a e power 5, and f phi of phi is equals to 1 by pi, where a ranges from 0 to infinity, where pi ranges from minus pi to pi. Densities of a and phi. So what we have assumed as a and phi are independent. For example, we have assumed x and y are independent in nature, where x was the what summation of a ai cos 2 pi f c tau I, and y was minus summation ai sin 2 pi f c tau I. Now, x and y were assumed to be not. When x and y are assumed to be independent, then we calculated f of a of phi, a f of a and phi. So that we have calculated. What we have assumed, so x and y independent, leading to a and phi also independent, where a is nothing but 2a e power minus phi is nothing but 1 upon 2 pi. So what is the probability that the attenuation of the channel is worse than 20 dB? How will you calculate? So H So what is the gain of the channel? Gain is a square. Okay. So if you calculate 10 log a square less than less than, now what is the probability that attenuation? Just we know and having the relation, so when a less than 1, bit error rate. Simple analogy, because in class I taught mostly about this stationary channel, how the relay feeding taken, where exactly the value should be. That is giving problems, so I am starting with this. What is performance analysis communication? So, in order to calculate the performance analysis, bit error rate is a metric which can be deployed to characterize the performance. So, what it is exactly? So, number of error bits received divided by total number transmitted. So, here BER is frequently expressed as probability. So, the probability of bit error, which is maximum possible bit error rate, is point. So information bits are modulated prior to transfer. So one such modulation format is given. Average power of modulation is P. So then 0 will be represented, 1 will represent. So detection at receiver will be, suppose the received signal is greater than equal, then it is 1. So that is 0 here, it is threshold based on the detection. That we know. Now, how we characterize the performance of wireless communication. Here we are having x, y is equals to x plus additive noise. So noise period, again the white Gaussian, then Fn by e power minus n by sigma by, then n 0 to 6 variance 1. As variance increases, so just giving the y is equals to minus root, bit error rate occurs when, since it is minus root p, so y should be less than equals to 0. The error will occur when y is greater than equal. So in that case, n, if it is greater than equals to, the probability bit error rate will occur. Because here the threshold is assumed as n probability of n, where we are having n as here 0 and sigma of a root of at 0, n by sigma equals to probability of it's a normalized Gaussian random is greater than equals to tail probability of, and it is equals to so here if it is tail probability, so x is greater than normalized Gaussian random, then it is called Q function. Here it is called. First we represent normal Gaussian random sigma square. Here if sigma is equals to 1. That's why the n by sigma is used variable. Because normalized Gaussian random variable is having by sigma square. It is nothing but SNR. Okay? Because noise power nothing but probability of bit error in AWGN average power P nothing but root 2 of root over transmit power divided by where P by sigma square is equal to. So example is that SNR is equal to what is the bit error rate for BPSK model. So in that case it is nothing of error rate when we are not having any leading coefficient, just AW is equals to wireline communication where bi channel are used. So we are not having bi channel is used. We are calculating this bit error rate. Bit error rate is not. Now for approximate calculation of Q trick of x is less than equal 1 by 2 e power minus x square by 2. The determinant of Q of x is equal by 2 e power SNR is 1 by 2 e power approximate b. So this formula is used of root over what the options were given equals to 1 by 2 e power because e power 1 by 2 e power square by 2 x. So what is the SNR divided for b here of just keeping e power keeping the values here. Now you may ask, we were talking till now we were talking about wireline channel. Now we will talk about Rayleigh fading because basically we saw fading coefficient where YT is h of and this h is not fading coefficient. And AIE and we assume that keep this h is equal to h if by where a was equal f a of a equal f of by no so by default we are assuming that here is the signal component h by fading channel and then it is adding to n. Okay. So receive signal is nothing but h of x plus n. Wireless communication system fading is there due to multipath propagation. the fading coefficient A e power. Okay, so far so good. So receive power here in this case is mod of h square into p. That case it was right, and one symbol was assumed to be and 0 was assumed to be minus root p in case of just BPS. So here it will be different. Mod of h square is nothing but a. Because here we are calculating some magnitude, but the C power is equals to a square into p. Fading SNR a square p a square into SNR. Fading SNR with fading is equals to a square into SNR. So from here it is derived for BPSK model. SNR of F, we can directly write it here. Here is nothing but equals to root. Here in case of fading, because we are having fading coefficient happening due to H, so A square will be multiplied. Now A square, which is depending on the fading coefficient H, is a random coefficient. Right? Random coefficient. So to find the average BER, we have to average with respect to distribution, which is depending on the random coefficient. So FA of A is equals to 2A e power A is a hence A is a random function. So we need to calculate average, the expected value. Average BER will be expected value. Since A also ranges from expected value of X is what? Right? Fx of f of X. Let's say f dash. So this f dash is this function A. That's why we will calculate the expected value with respect to A. So this is a Q function. So here it is Q of root over x a square SNR multiplied with f a of a d, because this is and since a ranges from 0 to infinity, a e power minus, and after calculating and all, getting here is equals to by 2 simple q 1 by 2 e power was there. Simple calculating here you after the average calculations, we'll be getting BR is equals to 1 by 1 minus SNR. We're getting BR is equals to average BER for BPSK and Rayleigh fading channel equals to 1 by 2, where BER for case of wire channel is root equals to approximately, right? In case of wireline channel, well, right? In case of BPSK only, well, fading coefficient. This is giving. Now, compute the BER of wireless channel system for SNR of this. So this is 10 log SNR here. We the value of SNR. Compute the SNR dB required for a BER of this. Yeah, right. For AWGN of wireline channel, the corresponding are required to achieve this. So therefore, achieve BER or to achieve BER of this is 14.9 dB. Therefore, for the wireless channel, the extra SNR in dB is 57 minus here. The compute SNR of BER of 10 power minus 6 is 57. And in order to achieve this, it is just a minus. Required SNR achieves the same BER wireless channel. In case of this, it was in case of wireless is 57, SNR is required. Whereas in case of wired channel, it was 14. So if we see the difference, there's a huge increase in SNR in a wireless channel to achieve the same BER because of the fading, all thanks to fading coefficient. So let us examine the reason for this, because BER in case of wireless channel is nothing but so just giving properly and approximating. So BER is inversely proportional to SNR. BER in wireless channel is inversely proportional, whereas in case of wired channel it was decreasing with respect to exponential. So exponential is this and linear is this. There was one question in assignment. So in case of exponent, in case of that there was two graph given, and it was asked how the BER and SNR curve will be. So BER or SNR curve in case of wired channel, it is exponential, where the BER SNR curve in case of wired is linear, all thanks to fading coefficient. So exponentially decreasing is okay with respect to linear, not decrease gradually as it, because inversely proportional to SNR. So using the formula for approximate BER, calculate the BER of this in case of wire. It is coming 57 dB. Approximately. BER of a BPSK BER of BPSK in wire relay interpretation. Approximate expression is 1 upon 2 is and by 2 SN. Poor performance wireless channel is due to deep fade, when actually the deep fade. So when drastic deep the fading channel model was I is equals to deep symbol, transmit symbol, the C power P is A square. System is in D fade if the signal is low. A square very less. So when the system is when A is less than root, probability of D fade is not A is less than equal. It is equals to 1 minus e power minus 1 by SNR. Now there is an analogy behind every formula. So how to calculate also. So this formula is very well known. Probability in D fade, that is directly used in the calculation. So in the calculations, if it is directly used, it's nothing but 1 minus e power minus, right? Because 2a e power minus a square is the probability density function of the ray fading, And when the defade is happening, when the signal power is very, very less than noise power. Signal power was nothing but A square into P, right? So when A square into P is less than sigma alpha, so A is less than root over 1 by SNR. So when we calculate this, the root over probability of defade 1 minus e power, and it is high SNR, it can be, yeah, when it is one by S like or lower order, it is high SNR. Probability of defade at high SNR, high SNR. What is this? Like 1 minus for SNR plus SNR, what that probability of, and when we approximated it, it was coming around 1 upon 2 by SNR, right? Now probability of defade is also at high SNR, it is 1 by SNR, because probability of defade is nothing but e power minus 1, right? So the bit error rate is directly proportional to the probability of good expression that we can see. So the bit error rate is directly proportional to probability of defade. Poor performance of wireless channel arises from destructive interference. To improve the performance, diversity. So what is happening here? We started with simple wired channel. In case of wired channel, what we observed that the probability of bit error rate is nothing but of root over SNR. Okay, that was our analogy. Now, when the fading coefficient came into picture, in that case, it was H was also one term that came. So y is equal to hx plus n. In that case, probability of bit error rate is equal to a square into SNR. Since a is a random variable, so we did integration. Why we did? We calculated the expected value with respect to a, and after that we got 1 by 2, 1 minus root of plus 2 plus SNR. And in that case, it is equals to, when we approximate it, it is equal coming to 1 upon SNR. And in case of wired channel, it was coming around 1 by 2 e power minus SNR, 1 by 2 SNR. So it was exponential, where it is in case of wireless channel, it is linear. Now we calculated probability of defade. So probability of defade when the SNR value of the signal is very, very less than noise power. In case of noise power, when we calculate the probability of defade, because as we know, the probability density function of the attenuation, which is equals to 2a e power minus y, and that is where the actual signal comes into the picture. And what we found is probability of defade is directly proportional the bit error rate, probability of bit error rate. There our analogy comes from, and in order to improve this, the diversity and defade events are we all talk about relay fading, relay fading. So in case of fading, we are having three types of fading. We talked about relay fading mostly. average BR via moment generating function is given like this. BPS, these are the form of the derivation. Diversity can be employed to overcome fading, overcome the effect of fading. So, di- the principle of diversity, if the single link is indeed fair, the performance will be bad. So, why can't we have different links at the same time? But here, the MIMO is different. How? Because in MIMO, you are transmitting different messages via different links, but in case of diversity, you are transmitting the same information over different links. So that if any one of the link is not proper, you can deploy, you can transmit the same message over link, and in that case, if the one link is defair, it will be transmitted to the other link. So consider the system with different link with multiple links. Okay? So there's a diversity in the system. So example of diversity, like antenna diversity. Here we will be having MRC concept. Link 1, link 2, diversity reduces the fading coefficient between T S2 is fading coefficient between Y1 is equal to sigma Y2 is equal the model Y1 is equals to H1 X plus. This is a fading coefficient where H1 you might understand or misinterpret H1 with respect to impulse response, but impulse response cannot be directly multiplied ever the time domain. The impulse response is but the convolution. They're having two links and పడ్డది